monitor for a while. Is
Yes.
it good enough?
It's good in presentation mode. Thank you, Kyriakos. You can start.
Okay. Okay. So hello everybody. Good morning or good afternoon, depending on the country where you are connected from. My name is Kyriakos Giannakoglou, and I will be very happy to present you this material on compression methods for adjoint-based optimization of unsteady flow problems. It is a piece of work done at the National Technical University of Athens in the School of Mechanical Engineering, and in particular into the parallel CFD and optimization unit. And I would like, first of all, to acknowledge work done by my colleagues Andreas Margetis and Dr. Vangelis Papoutsis on this topic. Of course, everything has been done, or almost everything, in the context of the exaFOAM EuroHPC project. So, sorry, it seems that I have a small sorry, it seems that I have a small technical problem. Am I connected still, Flavio?
Yes, you're connected. We are seeing your camera.
You're still seeing my first screen, I think.
We are seeing you, but
okay. I don't know what is going on, but I'll make it. Okay, it works. So,
yeah.
Let me explain to you as briefly as possible what is the topic I'm going to describe here. I'm going to talk about shape optimization in fluid mechanics, in CFD in particular. For instance, someone wants to optimize the shape of the car. And when someone says to optimize the shape of the car, we mean, for instance, we want to reduce or minimize the drag, increase the downforce, and so on and so forth. What do we need to run a gradient-based shape optimization in CFD? Practically, we need 4 different items. The first of all is to have access to a good flow solver, a CFD software, in fact. And thanks to God, in OpenFOAM, we have everything we need to do our job. The second thing is to have a shape parameterization technique in order to parameterize the shape we want to optimize. And the parameterization technique will define the design variables or degrees of freedom, practically the set of unknowns that the optimization method is going to compute. We also need to have some objectives, at least one objective and some constraints. And on top of that, we need to have an optimization method. Regarding optimization method, we might have access either to gradient-free or gradient-based methods. In this talk of mine, I'm going to focus only on gradient-based methods, and I'm going to talk about the adjoint method, the continuous adjoint method. Some of the tools we're going to use here can be found in Adjoint optimization form, the publicly available library our group has built and made available through OpenFOAM. Okay. So, about parameterization. What is parameterization? I'm trying to explain a couple of things for those who are not familiar with them. There are plenty of different ways to perform a parameterization. For instance, here we are using morphing techniques based on volumetric B-splines, which practically means that we are using a lattice. The lattice, as you see here on the left for 2-dimensional cases, on the right for 3-dimensional cases. introduces some control points, and whenever we are moving these control points, we are practically moving simultaneously both the shape to be optimized and also the surrounding grid. So for us, the design variables, Bn, are the coordinates of some of the control points. I'm saying some of them because some other might remain fixed. For instance, in this car application that you will see later on, the blue control points are fixed, they do not move, whereas the red points are moving, and this determines the design variables. In a gradient-based optimization, I skipped one transparency, let me go back. I'm going to talk about the adjoint method. And some of you might not be familiar with the adjoint method, so allow me to take only 1 minute and explain to you what the adjoint method is without mathematics. The adjoint method has been inspired by control theory, and its role is to compute the objective function J, the gradient of the objective function J with respect to the design variables as defined by the selected shape parameterization. Why are we working with the adjoint method? Because this is the only one that can compute the gradient of J with respect to Bn without first computing the gradients of all flow variables, such as pressures, velocities, turbulence, quantities, whatever, with respect to the same design variables, and then use them to compute the gradient of the objective function. What is the computational cost? The computational cost is the cost for numerically solving the adjoint equations, and this cost is practically equal to the cost of solving the flow or primal equations, for instance, the Navier-Stokes equations. So overall, if we want to compute the gradient of J, the cost is twice as high as the cost of solving the Navier-Stokes equations. And the most important, and the reason many industries, practically all industries, rely upon the adjoint method is that this cost does not scale with the number n of design variables. There is a last point I want to discuss with you, is whether we are going to use discrete or continuous adjoint. If you look in the literature, you will see that some people are using discrete adjoint, some other people are using continuous adjoint. The first one is the technique in which we first discretize and then differentiate our equations. The second one is the other way around. Here, even if this lecture is exclusively based on continuous adjoint, the presented methods can equally apply to discrete adjoint. So any kind of optimization method can profit of the techniques I'm going to present you. How does an optimization loop look like? We start by defining the design variables. Then we are solving the flow equations. We are computing the flow field. We are computing the objective function J. Then we are solving the adjoint equations. And using U, the primal solution, and psi, the adjoint solution, we are now ready to compute delta J, delta Bn, which is the required gradient of the objective function. Using delta J, delta Bn, next step is to update the design variables, update the surrounding CFD mesh, and then go back and repeat an optimization loop. What is new in this lecture is flow unsteadiness. There are some cases, such as, for instance, the flow around a typical passenger car, in which we cannot do this study by just using a steady solver. Why? Because there are vortices developed behind the car, and a steady solver cannot converge in such a case. So unavoidably, someone should rely upon an unsteady flow solver. And in case we are solving the unsteady primal equations, the unsteady flow equations, It is also unavoidable to solve also the unsteady adjoint equations. The important thing, however, is the following. What you see here is the flow equations on the left, the adjoint equations on the right. And the important thing, allow me to repeat what you have seen before, is that whenever you are solving forward the primal equations, then you are obliged to integrate the adjoint equations backward in time. What is the meaning of that? The meaning of that is that when you integrate backwards in time, when you are integrating the adjoint equations backward in time, then you should have access to all instantaneous primal fields like pressures, velocities, turbulence. So if you are ready to store everything, then this means that the memory requirements will be significant, and perhaps in large-scale problems, you cannot afford it. What are the known ways right now to handle the so-called unsteady adjoint, which is a real challenge to all people working in this area? Practically, there are three known ways to do the job. The first one, you see it on the right, is to work with full storage, which practically means that you are going to store all the instantaneous fields computed during the forward in time integration of the flow equations. Of course, this technique has the smallest possible cost, but at the same time, unfortunately, huge memory requirements, especially in large-scale problems. To give you an indication, to quantify what I'm saying, we need about 0.6 terabyte per million cells per 10,000 time steps. This is the blue box you see here. On the left, you see the other extreme technique, which is called zero storage. Zero storage means that we are not planning to store anything. Instead, we are going to recompute all flow solutions anytime we need them. So zero storage, but huge recomputations that make the whole optimization turnaround time extremely high. Practically, it is only for the sake of completeness that we are putting zero storage and full storage in such a slide. Practically, in large-scale applications, nobody wants to use them. So the industry uses a middle ground solution, which is the so-called checkpointing or binomial checkpointing in specific. What is the idea here? The idea is to try to relax memory requirements with a controllable computational overhead. That is, while integrating the flow equations forward in time, it's better to go to the next slide, while so integrating the flow equations forward in time, some selected instantaneous flow fields, the red points you see in this graph, only these are stored at a number of optimally placed checkpoints along the time span. To retrieve flow fields at time instants other than checkpoints, what you have to do is to use the flow solver to integrate again the flow equations forward in time, starting from the last checkpoint. It is for sure that already used checkpoints should be relocated into the time span. Sometimes, if you want to further mitigate memory limitations, part of the checkpoints might be transferred to a larger, of course slower, okay, it is larger but slower storage area, such as the hard disk of your computer. This is practically the binomial checkpointing technique, what industry is doing in this kind of things. The new idea, and now I'm going to the thing we have developed in exaFOAM. I spent some time for the introduction because I might guess that some people are not familiar with all these things. The idea in the work we did as a group in the exaFOAM project is to profit of existing compression techniques or develop some other compression techniques in order to store everything or almost everything, you will see all these things later on, in compressed form and save storage and the computation cost. And we are planning to use both lossless and lossy compression techniques. You know, as I said before, some compressor tools were available and known before this work. Some others should have been devised, and they have been devised during this project, because I have to admit that the exaFOAM EuroHPC project was a great opportunity for us to do so. Before going further, I have to introduce the so-called IPGT Z+ compression kernel. What is this? This is a combination of three techniques. Their names are incremental proper generalized decomposition, or IPGT in short, ZFP, both of them, you see them in green here, are lossy compression techniques. ZFP pre-existed, IPGT has been developed by us. And the third one is zlib, which is a well-known, in computer science at least, lossless compression technique. Their combination, and you will see how this works in a bit, is practically the heart of all developments that follow. I will not stick with mathematics. Allow me to say a couple of words about proper generalized decomposition. PGT, in short, approximates a flow field depth using a finite sum decomposition, such as the one you see here on the left. It is practically the sum, including m terms. M is the number of modes, and this is user-defined. Each term is the product of x, which is the spatial mode, and t, which is the temporal mode. Here, we should be careful because we are talking about unstructured grids. And though someone might think that x is the coordinate of a node, no, this is not the right thing to do here. X is just the cell ID. So T is the time, but okay, PGT pre-existed, of course. We have not developed PGT, but what we developed, it was the IPGT, the incremental PGT method. In its incremental form, IPGT, the instantaneous flow fields are all compressed at the end of each time step by updating the already available modes. At the same time, the memory holding the instantaneous flow fields can be freed. This is the idea. So we have here in blue what has been already compressed, and in green what the new instantaneous field that should be appended to the previous one. I don't need, I think, to spend time discussing about ZFP and zlib. These are standard compression algorithms. The first one can be either lossy or lossless. However, here it is used in its lossy variant. Zlib is a lossless compression library that implements the so-called deflate algorithm. There is something more that we added in this work. Otherwise, I could say that we are putting all these methods together and we are compressing the already computed instantaneous time instance. This is not true. We are doing something more than that. Practically, we are coarsening our time horizon, you see it here, by defining a number of time windows. Why? Because as the number of steps, of time steps, becomes higher, you will realize soon that more temporal modes are needed in order to maintain an acceptable error. So this will increase a lot the requirements of this method. In order to reduce the cost, the time domain is partitioned into a number of time windows. Each time window is marked here with a green light. So practically the user defines a number, let me call them K of time windows. And the advantage here is that for each different time window, some might have even a different number of modes M. So for each time window, if you see here on the right, we are first using IPGT to compress everything. The modes, spatial and temporal modes computed by IPGT are additionally compressed in a lossy way by using ZFP, and the outcome of that is additionally recompressed using ZFP. We will see what are you gaining in a bit. Based on this algorithm, IPGT-Z+, we have devised two different methods. The two different implementations of IPGT-Z+ are, the first one is called compressed full storage, CFS. The idea is as simple as that. Do whatever you are doing with full storage. However, let us keep everything stored in a compressed form, using what else? IPGT-Z+. This is the so-called CFS algorithm. So we reduce the storage requirements, and of course, as you will see, we reduce also the cost. Next to this, in order to additionally profit of checkpointing, we have developed a second method, which is called compressed coarse-grained checkpointing, or 3CP in short, in which case we are applying checkpointing in time windows this time, and what we get from checkpointing is compressed using the IPGT-Z+ algorithm. The one is here and the other is there. If you look in the storage cost plane, and you will understand why after seeing some examples. I'm going now to the examples that we have run within the exaFOAM project or perhaps outside exaFOAM in order to understand the expected gain. And we have selected 7 different cases. Here you see 4 of them, case 1 to case 4. The first one is a motorbike. If I'm not wrong, it is the same motorbike used by Simone in the previous lecture. And then we have 3 other car shapes, like the derived, a known test case, benchmark case for the automotive industry, ID3, and CHR provided by Toyota. Why have we selected so many cases? Because in each of them, we have some different, first of all, grid size. We are starting from 1 million cells and we end up with about 40 million cells, or we are also changing the number of time steps for 10,000 up to 40,000 time steps. We have different time steps, different optimization methods. In all of them, we are using the URANS and Spallard-Talmaras and the corresponding adjoint method. And as you might see in the last row of this matrix, we have a different number of cores from 30 till almost 1,000. Why? Because we have different requirements. It suffices here to multiply the number of grid cells with the number of time steps and understand the volume of information you have to store in all these cases. Just to show you a beautiful picture, what you see here, for instance, is the unsteady flow around case 2. And what you see here in the second row, what you see here is practically the error we are making after just compressing and uncompressing the computed velocity. You see that the error reaches marginally 5%. And the same thing here. So we did something very, very simple. First of all, we investigated that compression and then uncompression is practically turbulence. Then we performed the optimization once without compression at all, and second with compression, with the compressed full storage CFS technique. And you see here in these 4 graphs the convergence of our optimization algorithm. In all cases, you see that with or without compression, we practically get exactly the same gap, which is an encouraging result because it shows that compression does not affect the convergence of the optimization algorithm. Or in other words, that it is absolutely safe to perform the optimization with compression. And by running this algorithm, we optimized the shape of motorbikes or cars, as you see here in this combined picture. In all of them, on the left of the vehicle, you see the starting geometry, like this one, and on the right, you see the starting geometry, and on the left, you see the optimized geometry. So we are very happy with these results. Let us see a little bit if quantitatively we have really improved the objective function. And as you see here in this combined plot, I tried to combine everything all to present all these test cases together. Why? Because the message is not if we can improve or not a car in each particular application. The takeaway message for you is that all these methods work, I would say, perfectly. For instance, here you see that in all cases, the average drag, you see it with the blue line, goes down. And overall, we are happy to say that drag has been reduced by about 6% using compression. This is a table in all these cases that compares CFS and 3CP, the 2 compression algorithms we have devised, with standard checkpoints. And here within the parentheses, you see the number of checkpoints. How have we defined the number of checkpoints? We defined, in some cases arbitrarily, the maximum allowable memory on our system. For instance, here for the motorbike case, we made the assumption that we have only 64 gigabytes available for this case. So the available storage determined the number of checkpoints. And we tried to run all these algorithms, standard checkpointing, CFS, and 3CP, and make some comparisons. There is no reason for you to stick with this table, though the table is here for you. I have summarized everything here on the right. If we compare the 2 new algorithms with standard checkpointing, you will realize that the memory has been divided by more than an order of magnitude, depending on the method, with CFS between 4 and 35, with 3CP by 20 up to 60. And the CPU cost has been reduced either by 30% or by 5%. Of course, it would be much more nice for me to compare everything not with checkpointing, but with full storage. In this case, you will see that at least the memory has been divided by more than 1,000 in many cases, by 3 orders of magnitude. 3 orders of magnitude, saving storage requirement. It makes the difference among 2 cases, that either I can solve this problem on my hardware or I cannot do it. With this compression, I can use my limited hardware in order to run highly demanding cases. And you can see this plotted in this Pareto-front-like plots in all these cases, in 3 out of the 4 cases, showing exactly what is happening and the reduction by comparing everything with standard checkpointing. Before closing, I would like to add something more. Sometimes, you know, the automotive industry is not so happy by running URALs. For them, sometimes this is a low fidelity model. They are very happy to run LES or DDS. In this case, all these methods are more challenging for 3 reasons, and they are listed here on the left. We have highly fluctuating flows. We have more resolved spatial scales and intense temporal derivatives. These are big challenges regarding compression. So we selected case 5, case 6, and case 7 to be studied again with LES or DDS. The one is a lightweight concept car designed by Toyota. The second one is the CHR, well-known model by Toyota. It's just the half car. And K7 is the same car in full configuration. You see also the boxes, the parts of the cars that are optimized. Here you might see how more challenging is to compress this almost chaotic flow that is developed in the rear part of the vehicle. And we made all these computations, and to cut a long story short, I can directly go to the right of this picture, in which you see that we have divided the memory, say, on the average by 10, compared to the standard checkpointing technique that is already quite parsimonious techniques regarding memory requirements, and we have divided the CPU, we have reduced the CPU cost by between 30 and 4%. And of course, if we compare everything with full storage, then the gain is huge. So you can see here, before going to my closure, you can see here the gain presented graphically. On the left, you see the gain if something decides to work with URALs solvers. On the right, the gain if you decide to work with a much more sophisticated flow model, let me call it this way. In all cases, the message is that you have good reasons to work with compression techniques in unsteady-based optimization. To conclude, unsteady adjoint is extremely challenging because the adjoint equations should be integrated backwards in time, and so we should have access to all instantaneous flow fields during the solution of the adjoint solver. The idea is to compress the primal solution time series, and this is extremely beneficial, both memory-wise and cost-wise, or to be even more realistic, sometimes this is the only solution if you need to solve a large-scale problem on an existing hardware. We presented 2 techniques, CFS and 3CP. They both work perfectly and reduce the cost and memory requirements of a steady adjoint. If both of them are based on this package, the so-called IPGT plus lossy compression algorithm. This is the heart of both of them. And compared 3CP and CFS, 3CP is more efficient memory-wise, whereas CFS is a bit more efficient cost-wise. But the good thing is that both outperform standard CP. And don't forget that both methods are applicable either to discrete or continuous adjoint, or I kept this for the end of my talk. There is no reason for you to work in fluid mechanics. You might be solving any other set of unsteady PDEs in any other field of mechanics. If your problem is unsteady and you are obliged to develop unsteady adjoint methods and use them, perhaps compression is the only way to do your job. And before closing, I have to thank, first of all, BMW, which some years ago supported the development of the IPGT technique, then exaFOAM for giving us the possibility to develop the IPGT Z+ algorithm and CFS, and also the National Technical University for giving a PhD grant to the first author, Andreas Maggetis, who has developed most of these things. Thank you very much for your attention. These are two papers that you might consult in case you want to learn more about these methods in detail, and I will be very happy to answer questions, if any. Thank you, Flavio, and the rest.